Okay, so we're going to get started because of time. And today we are privileged to have my very good friend and colleague, former colleague, Dr. Dhiman Mondal. And he's going to be talking on improved space and polar geodesy through advanced technology and techniques. So in a short while, we're going to have Dr. Dima talk to us about his work, give us an update on what they are doing at Haystack Observatory, just a little bit of what he is doing though. So uh, we are very delighted to have you, Dr. Dima. So, but before we get started, I want to welcome some of us that are new here. I see that a lot of people, I think like 7 to 10 people join as a member. Because the form I sent online shows that we have some new members here. So if you are new and you would like to give a quick introduction of yourself, we can handle 2 to 3 minutes of that. So please um, take the floor to introduce yourself. Don't be shy. All right. Some people are sending me tests. Okay. So I will not waste time. I think people prefer to write on the chat. So if you want, you can see their introduction on the chat. And then moving on, I just wanted to inform us that CONGA now have a website. No, it's developing a website. So the website is in progress. Let me see if I can show us a preview of this website. And it's still in progress though. So this is not, this is our website. We are working on it now. All of our materials will be distributed or will be uploaded in this website. Some of our talks, this is one of our talks at this meeting, will also be uploaded on this website. So if you miss the meeting at any point in time, you can always, or if you need information, you can always go to the website to find out more about CONGA. So that is the good news we have with us, and that is exciting. And so if you are here, you want to present your work, please feel free to do so. Just send me an email or mention it in the meeting. That will be okay. And then we'll follow up on that. Yeah, so let me put my phone on this. And let me see what we have here. Now, just to remind us about what we stand for, we are here to build a network of people that can work together. That's what we mainly hold this meeting for, in order to get across different kind of people, particularly people around the sector we are interested to put instruments, GNSS instruments in, or ground-based instrument in general. So we want to meet these people. We want to also train and develop every member of CONGA for the ground-based instrumentation. So when these instrumentation are developed, we want to be able to identify who we are sending the instrument to. So this meeting allow us to do that by getting to know one another in this meeting. Another point that we always emphasize in this meeting is that uh, we are interested in ensuring the distribution and assessment or accessibility of data. You know, most data sometimes are not accessible. So we encourage people to share their data for science purposes. So those are the main three things that we do on this platform. So you are welcome to join us at any point in time. And as well, you can introduce your students because here is a learning place. We invite very renowned researchers, professors to give us updates on what they are doing. So this is a platform where your students and graduate students and undergrad students can learn a lot. So today, without further ado, I will introduce our speaker. Dr. Dhiman Mondal is a physicist and research scientist at the MIT Haystack Observatory. He investigates how Earth, Earth atmosphere, particularly water vapor, affects high precision space geodetic measurement from GNSS or GPS and very long baseline interferometer, that is VLBI. Work at supports his work as supports improvement to the International Terrestrial Reference Frame, that's ITRF. He also researches polar sea ice deformation and help develop GNSS buoy for the Arctic and Seismogeodetic Ice Penetrator SGIP for Antarctic operation. He earned his Ph.D. in geophysics from the City University of New York, where his dissertation used coral records and geodetic data to document the 1762 Arakan earthquake and highlight the megathrust seismic hazard in the Indo Burma region. Earlier in his career, he contributed to building Bangladesh first seismic and geodetic monitoring network through international collaboration. That's fantastic. So Dr. Dhiman joined MIT Haystack as a postdoc associate in 2018 and became a research scientist in 2021. He continued to develop methods and instrumentation, including work tied to VLBI Geodetic Observing System, BGOS, to advance precise geodesy and geophysical monitoring. So Dr. Dhiman, today I introduce him as my friend because we we share the same office as postdocs. So we used to share the same office as postdocs in those days, and we are good friends. And to top it all, we are now neighbors. So if I throw a stone, if I throw a stone, it will land at his house from my house. So, so that is how close we are. So, Dr. Dhiman, I will give you the floor without any further audio. Please feel free. Let me unshare my screen so that you can as well.
Okay, yeah.
Yeah, that's cool.
You have to let me share my screen, Jana.
Yeah, just go ahead. I think you have the.
Okay.
Mhm.
Do you see my presentation, Jana?
Yes, I can see. Thank you.
You can, yeah.
Mhm.
All right, yeah. So as Jana mentioned, first of all, hello everyone. I'm Dhiman Mondal. As Jana mentioned, I'm a research scientist at MIT. But before that, I think I'm a good friend of Jana, or Jana is my good friend. And as you mentioned, we used to share the office in 2018. So Jonah started a few months earlier than I did. And when I first came into the office, the first person I saw in that room, that was Jonah. And then, yeah, we are still a good friend. So, all right, let's go into the topic. So today I'll talk about some of our engineering and science work that we do at Haystack in the geodesy discipline. I think Jana once mentioned that your group, Jana, is developing a GNSS network, right, in the Central Africa region. So that's why I sort of decided that I'll probably, discuss our, science and engineering effort that we do here at Haystack rather than discussing one single project. So, just in case if you find it a little bit useful. So, for those, some of you probably know where we are. So we are not at MIT main campus. Can you see my screen, Jonah? Just to double check one more
Yes,
time.
please. We
Yes.
can. Mm.
Yeah. So we are really an hour away from the Boston main campus, actually. Let me change my pointer. Yeah, so this is Boston. We are an hour away. We are northwest of Boston basically, and we have this beautiful campus where we have this 37-meter dome. This is the ionospheric monitoring system. Some of you probably are really familiar with that, and then this is our campus. Really, it's a 1,300 1,300 acre campus. It's nice and green. It's a little bit quiet because we are a radio observatory, so we like to be in a radio quiet place. So it actually has three different main campuses. This is MIT, so the main entrance is here. This is the Westford Geodetic Antenna, and then we drive here in the Milliston Hill. That's the MIT Lincoln Laboratory extension of that. It's a DoD facility. They do most of the classified research, and then you drove a little bit more, and then we are at Haystack, and we do most of the unclassified research here. So open for all, basically. So it's a nice campus. While Jonah was here, we used to walk every day along this road after the lunchtime. I still do it, Jonah. So just for you to know. So yeah, so as I mentioned that we are a radio science observatory, we have actually four main disciplines here. One is the radio astronomy, then the space science, atmospheric science, and geodesy. So if you remember that big, nice black hole picture, and Haystack was a big part of that EHT effort that, you know, what generated that black hole, the shadow of the black hole that we call. And then our space science is the one that is, developing and maintaining the MOXIE. And of course, this picture is from, I think, Larissa's paper. It's monitoring the ionosphere. That's most of the atmospheric science group does. And I am in the group of basically, geodesy. So we mostly, study the the earth, the rotation of the earth, and then the deformation of the earth. And also, we extend that to the polar region, studying the ice and glacier. So basically, studying the dynamics of the sea ice. So in geodesy, I described that we have this, four main disciplines, basically. It's, technology, innovation, both in space geodesy and polar geodesy, and also doing the science that is, developing the methods. And yeah, so that's what we do in the geodesy science. Two main disciplines: space geodesy and polar geodesy. And I will describe a little bit how we do it here. But before that, about myself, Jonna mentioned that I studied coral before, and I take this opportunity to show this slide that for my PhD, I actually studied tectonics, but that's still using two different methods from paleogeodesy and modern geodesy. Modern geodesy is basically using the GPS with omnistar satellites and doing these corrections and measuring the height of the corals. And then paleogeodesy is basically looking at the corals, and these are porites. These are a special type of corals. Those are really sensitive to the sea level change. So if you track their growth, you can actually track the sea level change history there. So but for some of these, like these big coral heads that you see here, they're living above the ground, above the sea level. The first question you would ask that, why are they doing there? Because they're supposed to live under low tide level. And then so I studied that, and I found out that there was a big earthquake there in 1769, and I was able to calculate the total deformation, and I had some interpretation of that of what can happen in the future as well. So that was my past life, basically, in studying both paleo and modern geodesy as well. So I find that geodesy, it has tremendous implication in the society as well. So this is one example that I brought. I think it's from Kenya, and Dhahabu, she was the health worker, and she found that the nomadic women has highest mortality rate in that Marsabit County. So she came up with this great idea to track those nomadic women when they're pregnant, so that she can bring the healthcare to them. And she basically developed she developed some kind of wearable GPS tracker, and with that she was able to track them and bring the healthcare to them. And it turns out that she was able to reduce the child death rate by 40%, and immunization coverage increased by 80 to 85%. So those are the inspiring stories of geodesy, how it's contributing to society. It still inspires me. And the science wise, if we look at this curve here, and this is actually, I would say, this is an issue for our future improvement or motivation. That this is the sea level curve from the Colorado State University, where that shows the average rate of the sea level as 3.5 and plus minus 0.4 millimeter per year. And there is actually an acceleration component in it. But if you look at this, uncertainty is 0.4 millimeter per year. That is mostly, it's contributed contributed from not knowing the terrestrial, reference frame really well. So yes, in geodesy, we are doing it well, but I think we'd have to question ourselves that how well we are doing the geodesy these days. Do we need to improve it or not, right? But it says that we need to improve, these measurements, which is, the improving the global terrestrial reference frame. So for some of, I know there are some geodesists here. I was looking at the chat, and they said, "Oh, finally some geodesy talks." But for some of those who are not familiar with what geodesy is, if I'm pretty sure you mostly are, but it's basically knowing where I am on the Earth, and how well I know my position, and finally how frequently do I know it, right? So those are the three simple questions, 101 level questions that geodesy basically deals with. And if we have to look for a definition, it's basically studying the, Earth's, shape and rotation and gravity, right? Including their evolution over time. And we want to do it because we want to monitor our dynamic Earth system. As you can see in this picture, the Earth is, even though it looks nice, but it's, geologically, it's really dynamic. It's changing every day. Earthquake is happening here and there. And then, um, sea level, that there are tidal motions, ice melting, all sort of things that are happening. But we'd have to monitor them with higher level, high precision and a high level of accuracy. Right? And the one thing that enabled this is called, International Terrestrial Reference Frame. I will discuss it in later a little bit. And the reason, we'll discuss it because this is one of the main, goal of Haystack is actually, my research too, that how do we improve this international terrestrial reference frame, through, instrumentation and also from the methodological point of view, right? So, we need to, to monitor our system, or even for the society, we need this, geodetic products, which is the, position, that how well we know ourselves, our location. We actually need it in different time scale. So this graph that I took from one of this report, x-axis is the time scale and y-axis is the precision needed for different types of applications. And you can see that, for aircraft navigation, car navigation, or the type of work that the hub was doing, you are probably, okay with 1 to 5 meters, accuracy, right? And that's, in a seconds, time scale. But as we go to the right side, there are more sophisticated observations that we need to make, like sea level, seismic hazard, geodynamics. And we probably need to know them, 1 millimeter, precision, or even, precision wise higher than that, right? And this red curve here it shows the goal, from the decadal survey mission. This is what we want to achieve in future. So basically, we want to bring all those all those application names right on this line. And this is what we are working for, by day, so that we can have those data with, that sort of precision. So yeah, and how do we, achieve that? So it's this inverted triangle, says the whole story. You would need a geodetic, infrastructure, that is, meaning, for now it's SLR, VLBI, GNSS, and I mean, and DORIS. And then once you have that, that can ensure that you have a better terrestrial reference frame. So that is basically knowing the origin of the planet and the scale and the orientation of the axis and that sort of stuff, which is basically defined by a set of, station coordinate, if you're familiar with ITRF 2020 map. And that enables you to do the primary geodetic products, which are the, precise, position, gravity field, for example, the orbits of the satellites that you're using. And I know there are many people here who are doing the atmospheric studies, right? So even for you, knowing the satellite orbit is probably needed. And then once we know that, and then it enables us to do better, geophysical, observations. And with that, we can do better geoscience. So that's the whole goal. So we are at Haystack, basically, we are, sort of at the base of this triangle where we are improving this geodetic infrastructure, improving the terrestrial reference frame, and also we are working, with different projects to improve these other products as well. But given that we are a radio science society, radio science observatory, we mostly deal with, VLBI and GNSS, yeah, in our geodesy group. just to give you an example that or a little bit of introduction of what terrestrial reference frame is. It's basically, saying that if you have to define your planet Earth with a three-dimensional system, how would you position the X, Y, Z axis? What would be the origin? What would be the orientation? That kind of stuff. And we would need that because everything else on this planet, even on the orbit, that's actually reference to the origin of that center. And we decided that we'd have to know the TRF with 1 millimeter accuracy and 0.1 millimeter per year stability if we want to get better geodetic observables in the future, right? And we combine it using 4 different techniques. VLBI is the very long baseline interferometry. SLR is the satellite laser ranging that shoots the SLR laser to the satellite and measure the distance. GNSS, you know what it is. DORIS is just the opposite of GNSS. It sends a signal and the satellite receives the signal, and from the Doppler shift, it calculates the location. So we combine the data from all those 4 techniques and sort of generate a one combined TRF. So you can have TRF, terrestrial reference frame, using one of those techniques, but combining these all 4 techniques bring strength to it. I mean, if you combine with, like this is a cartoon that shows, why you need to combine those. Independent GNSS would have like independent solution of the TRF. So what we do, we bring a tie point. The tie point could be the vector measurement between 2 systems at the core locations, where in those places where you have like multiple techniques together, as you can see here in this map from ITRF 2020 paper, that there are many places where there are multiple techniques, and you can measure the vector between these two, and with that you can tie the solution. And when you tie the solution, you come up with this unified technique, unified TRF. But the problem is that it's not so easy actually. One of the limiting factor was the tie inaccuracy. It's just because that for some of the techniques, for example, VLBI, very long baseline interferometry, it's basically difficult to find a physical measurement point which you can measure. Okay, there is a theoretical center of reference, but there is nothing really physical center of reference. Same for SLR. So in even previous solution, we sort of looked at that there are like 50% of the ties, they have less than 5 millimeter accuracy, and what it means that they have more than 5 millimeter accuracy for 50% of the ties between GNSS and VLBI. What it is saying that if you have VLBI and GNSS stations at a location, then you can the measurements that you have, that's more than 5 millimeter for 50% of those measurements. So we at Haystack, we came up with a different idea actually, that how do we improve those tie measurements at those collocated sites where you have multiple techniques together. If you look at this, that when this is VGOS or VLBI, GNSS, SLR, they sort of receive the signal from quasars of the satellite, but the signal passes through the common troposphere. So what we experimented with that, given that the techniques, those are collocated within few meters, what if we treat the troposphere as one single cell instead of solving troposphere differently for all of this location. So this is, well, one of my paper that is still, it's in preparation. But what we find out that if we solve for a common, tropospheric parameter for all of this, instead of solving, independently, then it actually reduces the scatter of the baseline length. So the current approach is that we use only position constraints; those are localized. But what we are saying, the atmospheric constraint, meaning saying, hey, there is no, when you are solving for the geodetic parameters, saying that given that the signal is passing through the same atmosphere, there is no difference, right? So, and we can see that 2/3 of the baseline actually it's improving, their baseline length repeatability. So that is one contribution towards making the ITRF more stable. It's still in prep though. So as I mentioned that we need 4 different techniques, and we need 4 different techniques because we harvest different strength from different techniques. For example, GNSS is everywhere. So the density of the techniques are basically the strength when we, combine into ITRF. And VLBI, it's the only technique that can give us all Earth orientation parameters together, all 5, scale, rotation, polar motion, and etc. So at Haystack, we actually, we work with this, very long baseline interferometry technique. So it's basically, it's 2 antenna big dish that are looking at the delays coming from the quasars. Those are the active galactic nucleus far, far away. So we receive the signal, we correlate and calculate sort of the delays, and then we can, calculate the distance between those 2 stations, and that can help us to determine the rotation of the Earth and the polar motion of the Earth, and that kind of stuff. So we are at Haystack, we actually developed this technology. We are still doing it, is what we call VIGOS. This is the new generation VLBI global observation system. The previous system was the legacy system. It has large dish, but it turns out that it's a little bit slower, and atmosphere is one of the limiting factor towards the accuracy. And we realized that, we can come up with a smaller dish that moves faster. That means it can sample sky more, and it can resolve more. You can solve for atmospheric parameter, more parameter, and also it's broadband. As you can see, the legacy system it has 2 band, and Vigos had like 4 band. So you have better accuracy there. So this is our main one of the main research project here to which is from the engineering science and also from the science side, that how do you build a better, bigger system so that we can observe our system a little bit better. So yeah, we have been doing it for we have been doing it for quite a while. So that's basically we are involved with developing the front end, the receiver, and the digitizer of the signal, because you receive a huge amount of signal, then we correlate that and we sort of generate, or we can see the improvement that we made. So these are this graph shows the group delay, which is the primary observable for bigger system. VLBI system. It is showing the group delay uncertainties, median uncertainties. And as you can see that the Vigos is really smaller. So meaning that we know these observations better with this new system. So we are claiming that we are improving it a lot. And it's not only the observables that are improving, we are also improving the product, geodetic product. Here you can see that the baseline, I'm showing the baseline length repeatability between Westport and Betzel. So that's about It's from like 1985, but as you can see, the length is, if you look at the scatter is sort of like, diminishing here, although there are some seasonal variation. But the error bar of these estimates is also reducing over time. And it's capturing the opening of this mid-Atlantic ridge. So it actually says that how much we are improving. And if we look at this graph that I took from Nielsen, who basically compared the Vigos and SX site repeatabilities. So these are the east-north up repeatability for the previous VLBI system, which are basically at like 5 to 30 millimeter weighted RMS. And for Vigos, it's almost like 2 to 7. I'm sorry, the y-axis for those, for two graphs are a little bit different. So we are, this engineering and science work is still been going on. We are not, right now, developing in Fortaleza, which is in Brazil. So they had one system, which is the SX old system, and then we are developing a new system there. The engineering crew is basically they're leaving next week to install the new system there. But one of the things that is really important is once we install that, that's the engineering work. But how do we know? We need to know the distance between these two systems pretty well to tie the solutions as I showed before. So here, actually, our science research project here, advanced technique that, unless you tie them together, as you see that there are SX and Vigos, network. The SX are red, the Vigos is in blue. There are two systems really, but they are running independently. But we need an unified solution. So it's not only, having, reference frame, ties between two different techniques, but also within a technique, we also some discrepancies. And this is an example that, we proposed a technique. It's called mixed mode observation approach, where we ran both networks together, and we came up with an unified solution. And that shows that with this, you can actually improve the quality of the TRF. I mean, these graphs are, showing the TRF defining parameters. So this one is showing the translation, rotation, and scale. So translation is basically the offset of the origin. So as it shows that, if you use this new technique, which is blue, the translation is minimal from the best known TRF. And it's same for the rotation and same for the scale. So that's our science initiative. But once we do that, once we bring all those improvements, it's actually enable us to do some cool science. I can give you one example, which Jonah mentioned earlier, that this is the work that I was involved, back in 2007 or 9, where we first installed the seismic and GNSS network in Bangladesh. Here, all these red dots are, and these are the GNSS, as you can see, me installing the antenna, NetRS, installing the solar panel. So with that, we were able to, first document the deformation across this subduction zone, which is northern Sunda subduction zone, which was basically a matter of debate for a long time. And what we found out that we published in Nature in 2016, that there is some active deformation, active convergence going on between these two places. So if I have to interpret it quickly, that the places between this and that, these places are shrinking at a rate of almost 17 millimeter per year. So that's what a significant that was a significant discovery, and it happened because of this high precision GNSS observations, actually. And of course, a better reference frame. Now I want to move a little bit towards the polar signs. Is in the pole, we are doing the same thing. We are all, developing new instruments so that we can do some new signs there. So we have we have experiment both in Arctic and in Antarctic. So in Arctic, we had one experiment that had we call it SIDEX, Sea Ice Dynamics Experiment, and the goal of that project was to understand the ice strength and stress propagation. How do they break up the sea ice when they start melting and that kind of stuff? And for that, we basically had two objectives there. That whether of course, whether the goal was to study the ice mechanics and dynamics, but engineering wise, our goal was to see whether we can develop something that with which we can collect continuous high precision GNSS data, right? Whether we can transmit that data autonomously from Arctic, right? So that with minimal control. And also, whether we can have some sort of power supply that can uninterruptedly power that system. And this is the picture that is showing the Arctic sea ice. These are probably the multi-year ice versus the first year ice. But there are some constraints. We do not have, many flexibilities there. Of course, our cost was limited, right? Of course, we had some budget. We had to work on that, and we decided we'd use AstarX OEM, which is low power, GNSS board, multi-GNSS board. I think right now M3 is on the market. And also, we decided that we use Iridium satellites for data transmission. So the power budget, because it has to be a little bit lighter so that two people can carry, and that means we cannot have really big batteries and things like that. So we'd have to have small batteries. So we are constrained by the power consumption as well, and also the weight of the system. So this picture is showing the ice camp. I did not go. Some of our colleagues, they went there, and this is one of these systems that you can actually see the beautiful sun at the horizon. All right, so the system was actually look like that, and just for you to give a sense of scale, that was in 2018, so we are all masked because what happened at the time. We all were wearing masks. So just to give you a sense of scale, I'm 5'8" almost, and then the system, you can scale it. So it has 3 solar panels, so that we can collect the sunlight from all direction. On top, we had this GNSS antenna, which is top-count GNSS antenna, Iridium satellites for data transmission. And those legs are basically, they're supposed to go into the ice so that they can anchor this system, because the wind is really strong on Arctic sea ice. And then this box actually had all these instruments in it: the battery, the main board, and Iridium modem, GNSS system, everything. And we had to insulate it because the temperature goes really lower. So we wanted to shield that from extreme freezing temperature, so that we can power the battery when we need it. So we sent 12 of them in 2018. And so this is sort of, you can see the scale. This is about 12 kilometers, X and Y axis. So they spread over different types of sea ice, and this is just a cartoon of what it looks like. This is the real. This is not. I'm telling you in the beginning. I photoshopped it just to show that what was the main goal. So the goal was to sort of capturing this lead opening and ice dynamics. But it looks like that we can do other things as well, which we did not plan. But it looks like that we can also study snow depth, and we can study ICES and ISAT data validation with that. I will show you in a while. So we installed 12 of them here, and they sort of traveled almost 1,500 kilometers across Beaufort Sea, and I think it's ended its journey in the Russian territory, and we don't know what happened to the systems after that. Some of them they probably sank on the bottom of the ocean. So with this, there are we published this paper, which is my colleague Hutchinson from University of Oregon. She is the lead author of this, but with this new system, given that these are high precision, this is basically our systems are really here, and these are these were the single frequency GNSS receiver that was provided by someone else. But when it combined, and then when we look at the deformation, we found something really remarkable, that the deformation basically, so this graph is showing the length scale versus the deformation. If you have to interpret it, it's basically, you know, tracking the changes. Let me try to explain it simply. Tracking the change of the area of a given region, right? How fast it's changing in which scale. So the length scale is basically the square root of the area that you are calculating. So it's basically tracking the change of the area at a given epoch, and then that's how you're calculating the deformation. But I think the one thing that we found that sea ice deforms differently at different length scale. So for a smaller length scale, this is something remarkable. Less than 2 kilometer. It looks like it's higher than what it should be. So it's not really fractal. So that's one science that we were able to do it. The other thing that we looked at the GNSS reflectometry, and we looked at the snow depth. And this is some of you probably know, but this is a technique at which you can actually calculate the height of the antenna from the surrounding surface. It's called the GNSS Interferometry Reflectometry. There is a nice package developed by Kristin Larsen. So you basically, give a Rhinex file, and it reads the SNR of the observation, signal to noise ratio. And then with that, you can calculate the height of the antenna. So what happens that the GNSS receives the direct signal, and it also receives the reflected signal. Then the reflected, signals based on where they're reflecting from, it creates, interference pattern, which, translates into SNR. And then with that, you can basically, find out, what is the change in the snow layer, if you have snow, if you have vegetation, or the moisture of the soil content. This is a new technique. So one of our students, she applied this technique, for the SIDEX system. As you can see, this is the system. This is HR, which is the reflector height. And she found something really remarkable. This is one of the system this is the height of the surrounding surface from the antenna. As you can see, that early March, there was nothing. It's sort of, it looks like there is no change, and then something happened in June, July, and then again, it went to a stable state. So we are looking at, she looked at, some previous papers. This one is from Don Perovich, who studies the sea ice and deformation, and also the melt ponds on the sea ice. And she found that, at that time when the ice was completely frozen, actually the time scale here, x-axis and x-axis of this graph, they're aligned. So you can see this is May is sort of here and October is there. But this graph is showing the albedo, which is basically changing. Albedo is the reflectance from the sea ice that is probably changing as a factor of how much dry snow you have or how much, surface is exposed. So what you can see here that the snow actually, it starts melt. They start melting, after mid, June, July. So melt ponds form, as you can see here. And then there are melt ponds surrounding the surface. And then after sort of August, September, and it goes to, it refreezes and you still have the solid surface. So it's remarkable that how one single system was able to capture that evolution of melt pond. So Jonah, how am I doing time-wise?
Yeah, time is not on your side.
Okay, how much time I have?
Yeah, we can grant you like
5
5 or 10 more
minutes?
minutes. Yeah,
Okay, yeah. All right, so I'll wrap it up quickly
yeah,
then.
thank you.
So yeah, so that was our SIDEX experiment, and I decided to show this. We have other projects. I decided to show this because I realized that you guys are also doing an network installment, right? So I'll probably skip some of the slides and go directly to the directly to Antarctica now, where we are planning to study the ice calving process, basically how, what is causing the ice, to break up from the ice shelf. So, and we are mostly, targeting these infragravity waves that are coming, ocean waves that are coming and hitting the ice surface. And that is this low, very low frequency, low frequency, wave within, seconds to 5 minutes. And yeah, so as you see that this is high powered. This is a spectrogram of the seismometer data. This is high power frequent, wave here. So we came up with this idea, and there are people before, like Brommersky, they have done installation. They have installed many different seismometers there, but we came up, but some places where you cannot go, you cannot access, there are crevasses here and there. So we came up with that idea to, develop something which is, droppable, which is this SGIP system that Jonah mentioned before. We call it Seismogeodetic Ice Penetrator. So this is about, 11 feet tall, and the main component here, main science instrument here is the seismometer. And we are planning to, and we actually did drop it, 3 of them in this January. We dropped them from the helicopter. So there is no need of manual installation. You just go with the helicopter, drop it from it's actually, I have a model, which is this one that I'm holding. Yeah, so you go with this and you drop it from the helicopter. The main instrument is here is the seismometer, which is near the nose cone here. And then on top, we have GPS antenna to track the motion, iridium for data transfer. And it has all these primary batteries inside. Those are the lithium-ion batteries, and that were good enough to survive 1 year. So we dropped 3 of them. So this is our colleague Chester, and so you can see he's about 6'2". You can see that how big that was. So it was carried by the helicopter, and then dropped it, went into the ice nicely. And then it's sending data and it's coming to the haystack. So Chester is going back again to retrieve it this year and end of this year. So once we have that, I think we'll be able to, study this ice shelf from, we installed this, very close to the Kelvin front, where, I think they don't allow people to go manually. So we dropped it from the helicopter. So we'll have some, good data set to study the ice dynamics. So as of now, it's doing well. We we have some. So this is one of the system, and as you can see, all of us, we have about 20 people in the Geodesy team. They actually signed the top of this ice. And just to show the results, we have three systems deployed there, and it is just showing the, height, actually, delta height solution until March, January to March after dropping. So they're right here, and we have the previous experiment that other people did. Those are from this region. So yeah, we still have to collect the data and then process it and understand what's happening. But I really do not have a good summary, but I would say that our goal here at Haystack to improve the understanding of ITRF and ice dynamics. Those are two main disciplines here, through developing new technologies, instruments, and through developing new methods as well. Yeah, I'll stop there. Yeah.
Thank you very much, Dr. Dhiman. This is a wonderful overview of instrumentation and science applications. So this is really good for CONGA. We saw so many instruments that you are working on. That's really cool. Very, very cool to see. Before I move forward, do we have any questions in the house? We are a little bit over time, but we can handle 10 minutes over time, no problem. So far, we are learning. So, is there any question to Dhiman? Dhiman is able to tackle your questions. Is there anyone from Geodesy in the house? I know that most of us are geospace. I know if we have Geodesy, they will so much love this. But the general idea is what is important here. So, okay, we have one geodesy here. I can see yes there. Um, I think he's also uh, Sintayeu. Yeah, welcome. I think I'm seeing him for the first time. He's new to this team. You are welcome, Tintayo, if I pronounce your name very well. Sorry about that. But welcome all our new members. We also have Ahmed here. Um, Dr. Dhiman, that GNSS receiver panel that you showed, it's how much energy can you guarantee? Because given the condition of the climate in the Arctic region, I don't know how much hours of data you can have in one day.
Yeah, so I think yeah, I think it was we sort of it was 4 watts about average per day user. So it was well enough to power um, the GNSS and Iridium. So those are the main those are the main two instruments.
For how long?
Well, so
For the whole day? I mean,
so
because
during
you hardly
so
have
yes, in the polar region you have sunlight almost in the summertime
in
almost
the summer.
20
Okay, okay, good.
24/7. So it's charging continuously, right?
Right.
So
So this is
so
for summer project. You can do
this is
winter.
actually a summer project. Yeah, in the winter is nothing worked in the winter.
Mm-hmm.
Although we had one system that survived through the winter, and surprisingly, it woke up in the next March. So that was a little bit surprising. I think that system it was installed on the multi-year ice. So yeah, so that was surprising. But yeah, it was, we took into consideration that there will be, sort of thin layer of snow covered on the solar panel. Some portion will not be visible, right? Those kind of stuff. Otherwise, if you are here, one panel would have been, enough to power it and run it, through the whole night, right? Or 2, 3 nights. So that's why we have like 3 panels so that it collects, maximum amount of sunlight and charge the battery. The battery was like the 12 volt, heavy duty batteries, the gel batteries. So it was well enough to power those two science instruments.
Maybe,
And
okay.
yeah, the iridium was the power hungry ones.
Mm-hmm.
The GNSS was really minimal. It's like, I think it's like 550 milliwatt or something. It's really less. But iridium was the power hungry. I forgot what it was, but I think it's more than watt or something. So we sort of tricked it a little bit, so that we don't run iridium all the time, because GNSS is the way we configure it. It's generating Rhinex file, or it's writing the Rhinex file in every hour. So we programmed it such a way that Iridium would only run, over the hour. So that
So
we
yeah, you download your data at interval. Okay.
right, then it goes to the sleep again, and then
Mm-hmm.
after 1 hour, then it wakes up, and then it's uh, yeah, then it sends the data again.
Yeah,
So you
excellent.
have a question,
So,
yeah.
so you have battery with it, or it's just the panel?
No, it has battery in it.
Okay. Okay.
So the box has, that's why this box is a little bit bigger.
Very big. Yeah.
Otherwise it did not have. Yeah. So it has battery in it, and then then the charger, of course. Yeah.
Excellent. Excellent. This is
Yeah.
really, really good.
How are you doing with Conga? Did you design those,
Yeah,
or are you?
if you see the website that we are designing is coming out soon, or if it is not already out. So we show some prototype that we design. It is not all solar panel because, like you show here, because that is we have the equatorial region where we have sunlight every now and then and very high energy radiation. So we don't really need so much panels like this. So our panel is let's say less than half of what you are showing here. But yeah, that is really necessary for Arctic region. Also, in the future, maybe you will be thinking about covering the whole season, and you have to figure out the idea of running your system throughout the year in that case. So that you have a complete study or understanding of what is
I mean
going
that, yeah, I mean that is always the challenging case for all of these, all of the scientists, who study the sea ice,
on.
because during the summertime, you really have narrow window. Summertime the ice melts, right? And if you install something on the sea ice, unless it is on the multi-year ice, that instrument will sink, in the bottom of the ocean. In
Right.
the winter time, there is no light there. It's under complete darkness, right? So
Mm-hmm.
it's really, difficult to power, any instrument.
Right.
So we really have to rely in that case on the satellite observations,
Mm-hmm.
on ISAT and cryosat. So ISAT and cryosat, they goes through the winter,
Oh, I
but
see. Mm-hmm.
yeah,
Right.
but um, but the direct, I have one slide which I did not show, but another important implication for that project was that, we have some in situ observations, and that we can, when I brought it here, we can see that there are some disagreements with the satellite-based observations, meaning ISAT, CRISAT, they don't measure the sea ice thickness directly. You calculate or you estimate the sea ice thickness from the freeboard, which is the height, the floating part of the sea ice above water. And then you apply the physics, apply the equation of isostasy there. And then you calculate the sea ice thickness. But what we found that there is a large disagreement when, our project shows here, and versus what we see from the ISAT and CRISAT. So, there was another system, it's called IMB, Ice Mass Balance Buoy. So that measures the ice thickness directly. It has a thermistor chain by which you can calculate the snow thickness and the ice thickness. So you can really you can really validate the ISAT and CRISAT estimates. So that was, I think the implication was that data set it's still something it's very useful.
Yeah, excellent. So thank you again, Dr. Dhiman. And one more thing, this platform is also about making data accessible to research scientists or professors that have students that needs data. And given that you have multiple instruments that you are working on and collecting data, I was wondering, somebody here is interested in your data. What is the steps and how are the data availability like?
Yeah, I think our JGR has we submitted the data to the Cryosphere repository, so the data is available.
Okay.
If you, I can
Do
give you the
you
link.
do you make use of Madrigal data?
No, the material is for ionospheric study. These
Yeah.
are different ones. I
Okay.
mean, the Rhinex will be the raw Rhinex files will be archived in the UNESCO or CDDIS website in the future.
Hmm.
Some data, because we're still you know working on it with some of this data, but yeah, they are available through that paper. Those are publicly available. If you
Okay.
go and take a look at the Hutchison's paper that we
Sounds
published
good.
on.
Yeah, sounds very good. Thank you very much. Any other question in the house? I want to thank everybody. I see Babatunde Rabiu, Professor Babatunde Rabiu. Thank you for coming to this meeting again today. Bless. Thank you. Thank you, Yenka. I see Dr. Shigo right there too. Thank you, everybody. And this was a very nice presentation, Dr. Dima. Thank you for your time. And
Yeah, thanks
next
so
week,
much for inviting me. It's great talking to you all.
yeah, thank you. Next week, we have our in-house presentation from, let me see if I can bring it up, from Dr. Andrew Mizella. Uh, is going to be talking about total electron content determination for ionosphere and plasma sphere. And next coming month, which is our last presentation or meeting for the year, we're going to be having people from Kenya Geospace or Space Science in Kenya. They'll be talking about their instruments and all the technique they are using in that space agency. So we have very good and interesting seminars in the coming months. I want to invite everybody to join us again next month. And until then, I thank you. See you. Bye.
Thank you, Jonah. Bye.
Yeah, sure. Thank you. Thank you, Dhiman. Mm.